I can actually show you that with a real charged beam. So this is an evacuated tube, and it puts a big negative potential on this electrode. So high that it actually boils, electrons come off the electrode. It makes just a beam of electrons. It also has some a little bit of background gas that ionizes to keep everything stable and doesn't charge up too much. But mostly you have electrons flying off this electrode, and most of them go straight to this metal plate, and that's the end of the story. But there's a little slit in the plate, so some of them get through and make a beam that keeps going. So you've got a beam of electrons, and this little plate is tilted a little bit, so they slowly, along this direction, they crash into the plate. The plate has a phosphor on it, so it lights up when they crash into the plate. So when I turn it on, there you can see the beam. That's a beam of electrons flying through the tube. So what we're going to do is bring a magnet and see what it does to the beam of electrons. Because remember, this bar magnet, the field lines go from the north pole, the red is the north pole, to the south pole. So if we just think about the poles, or the field right at the ends, because we're going to use the ends, it'll be this way near the north, it'll be pointing in the south. So I will bring the north pole pointing at me at the beam, and let's see what that'll be. We have the beam going this way, and I'm going to bring this pointing in, so we're going to have a B field like this. So V cross B also the same as this. It should be up. Right? So let's see what happens. There's our beam, and I bring in this magnet. Oh, there's the deflection we hoped for, but it's down. And it's down. And why is it down? It's down because they're electrons. Right? Q, in this case, equals negative E. The charge is negative. When the charge is negative, the force magnitude is negative, which means it goes the opposite direction. Right? So right-hand rule says it's up for positive, but the force is down for an electron. So it did deflect the right way. It deflected down. We can also check, we can take and aim the south pole at the beam. So here we go, bring in the south pole, and there it goes, it deflects up. Just like you'd expect, because when you bring in the south pole, the beam, or the magnetic field is pointing the opposite direction. Now I'm bringing in a field that's pointing away from the beam. So it would seem that the charged particle beam really is deflected the direction that you would expect.